Okay, kids, today we are going to talk about properties of the definite integrals. Right? And definite integrals are the same thing as doing a derivative backwards, right? And we're going to get a lot more into that idea of undoing a derivative. But just like we had properties of derivatives, remember you had that the derivative of a sum or difference was the separate derivatives of the sums. Right, we're going to do, and we had the differences, we had right? So you would do something like if I gave you f of x is equal to x squared plus 3x plus 7. There were multiple rules you used on that. To find f prime of x, it's like this is one function, second function, third function. You use the bring it down property rule. You use the constant multiple rule. The derivative of 3 times the function x is 3 times the derivative of x to the first, which is just 1. And then the derivative of a constant is 0, right? You use multiple derivative properties to evaluate, given f, find the derivative. Well, we're going to go backwards, and instead of finding the derivative, we're going to find, right? We want to go from finding the derivative back to where it came from. It's going to take us a while, but so what we're going to focus on today is just the properties involved in finding the antiderivative, which is just a synonym for an integral. So we've talked about this before. When does an integral exist? Unlike derivatives, when do derivatives exist? Derivatives need continuity and smoothness, right? No corners, no cusps, no vertical tangents. All a function needs to be is continuous in order to integrate it. Absolute value, cube root with that vertical tangent, right? X to the 2/3 with those cusps. I can integrate all of those. All I need is continuity. So the order of integration is your first property. So take a moment to look at what that says. These two integrals are the same. What's different about them? Dx is the same. F of x is the same. The bounds are different. So what that means is, let's pretend you had some function and let's just stay above even though we talked about being below. It's easiest to visualize if I'm above the x-axis. There's where I'm going to start. There's where I'm going to stop. So remember when you think about drawing rectangles under here, right? And collecting infinitely thin rectangles and their areas and adding them up. So what's true? Your function heights are positive and you're going from A to B. So your dx, your widths are also positive. What happens when you multiply positive times positives? You get a number. So let's say you did all these infinite things and that number was 7. The area under that curve was 7 from A to B. Well, notice what this says. This says start at B and stop at A. What does that mean? You have the same rectangles under there, but you're moving through the domain backwards. When you're going along a domain horizontally and you're going left, what sign do we use with going left? Your dx is negative. But your function height is still what? Positive. What happens when you sum the products of positive times negatives? You get a bunch of negatives, but you're going to get -7. What if -7 is not equal to 7, but if I negate -7, so what this says is if you want the same value out of an integral, but you want to change the direction in which you integrate, you can do that as long as you pay the price with a negative out front. Crazy, right? This is a highly useful property. When is your area 0? And again, let's just imagine that we have, just for simplicity's sake, let's say we're above the x-axis and we go from A to B. And let's pretend all of that area, again, is 7. Because I had a bunch of rectangles, I went up to the function over, right? And my dx's were positive if I went from A to B. But what happens if I go from A to A? My function is positive, but what is your width? If you start and stop at A, what's your width? Your width is 0, and I don't care if you have positive or negative function values. I don't care what. If your width is 0, what is your integral? 0. That's handy a lot of times. I know it doesn't seem like it's going to be handy, but I promise you it is. Just like derivatives, there's the constant multiple rule. So if you want to integrate a constant, K is a number. Think of it as the dilation factor, right? The multiplier in front of a function, like 3x squared. 3 is the constant. You can integrate with that constant inside, or you can osmosis it outside the integral, right? Do you see where the constant ended up? So I can just integrate the function itself, draw the rectangles underneath the original function from A to B, and then multiply by my answer times the dilation factor. I don't always. Sometimes I leave the K in there, but it's handy sometimes. Those two things are equal. So constant multiples can either osmosis out that integral sign. Sometimes I want to osmosis it back in. Now, every year, I tell the story of one year I was talking about osmosising through like the integral sign, and I had this kid raise his hand and say, Miss Getz, isn't that technically diffusion? Because osmosis means it's water. And I said, be quiet. Osmosis is a much cooler word than diffusion, in my book anyway. I like to say osmosis. Sum and difference, just like derivatives. The integral of a sum or difference can be split up into the sum or difference of two integrals. Okay, swell. So in other words, what if you don't know how to do this, but suppose I wanted to integrate from, I don't know, 1 to 7 of sine x plus x squared dx. If I didn't know how to do that, I could say, well, this is the same as the integral from a to b of sine x plus the integral from a to b of x squared dx. Okay? If I want to split an integrand up, that's vocabulary. This is called the integrand. This curly Leibniz's sum thing is called the integral sign. But what's inside, in between the integral and the widths, the heights are called the integrands. Okay? So I have f of x is the integrand for integral 1. G of x is the integrand for integral 2. This statement works because you can't integrate unless you have continuity. So what it says is, if you start at 1, let's pretend this is 1 to 5, and if you add the integral from 5 to 10, that is the same thing as just integrating from 1 to 10. Here's a picture. Right? Because when you integrate, you are integrating under the same function. If you integrate from A to B and add the blue area to the orange, red, pink area, going from A to B and from B to C is the same thing as going from A to C. Sometimes I like to have 2 integrals. Sometimes I like to have 1. I can go either way. I can have 1 integral and break it up into 2, or have 2 integrals and break it up into 1, as long as those values match. Now, unlike derivatives, there's some properties that do not work. You really, really would like them to work, but they don't. You do not have a quotient rule for integrals, for antiderivatives. This is not true. Not true. You cannot integrate a quotient and just take the integral of the numerator and the integral of the denominator. You couldn't do that with derivatives either, but I gave you a quotient rule. There is no quotient rule for integration. One technique I will teach you later to deal with a quotient that doesn't always work. I will teach you something called U substitution, which doesn't always work. And I will teach you something called partial fractions, which hopefully you did in pre-cal, and it is a technique you need for this kind of integration when you have a quotient. It doesn't always work though. That's why there's no quotient rule. That's the thing with integrals. Unlike derivatives, I can give you any function and you should be able to take its derivative. Not all functions have an algebraic antiderivative. Kind of crazy. That makes me sad, right? I feel a little bit sad. There is also no product rule. It is not true that the integral of a product can just be broken up into separate integrals. This is not true. When I have a product, I will teach you sometimes you can do the same thing as with I will teach you an integration technique called U substitution. I will also teach you later an integration technique called integration by parts. But neither one of them always work for an integral of a product, which is why there is no product rule. If there was a rule, it would work every time I had a product. There is no rule. AP will test you on this knowledge, and I'll show you how in our handout practice. That makes me sad. So let's use some of our rules to evaluate these integrals. Even though you don't know how to integrate, I'm going to use some of these rules. And geometry. Okay. I've given you properties, but I haven't taught you how to integrate yet. So I want you to look at this, and I want you to draw a graph. We're going to start at 3, and we're going to stop at 10. What is the integrand? What is the height? Remember, an integral is a product of function heights times widths. Here is my width. Where is my function? Where is it? It's 1. Can you draw me a function on that axis that has a height of 1 constantly? So when x is 3, the function is 1. When x is 10, the function is 1. Everywhere in between, the function is 1. What is the area of that shape? Well, that is 10 minus 3, which is 7. With a height of 1. All because I recognized they were asking me to integrate a function whose height is 1. I have infinitely small widths starting at 3 and stopping at 10. What about B? Hopefully, you recognize that function, your integrand. This is from your summer packet. This is from the beginning in Unit 2. In our review, we dealt with this. If you look back at our Unit 1, when I gave you domain and range review handout, this function is on it. This is a semicircle with a radius of 2. Well, I know the area of a semicircle. The area of a semicircle, the semicircle is above the x-axis, and it's 1/2 pi r squared. My radius is 2. So this is 4 pi over 2, aka what? 2 pi. I'm so smart. Yay me. I'm so smart. That answer's wrong. That answer's wrong. It's not completely wrong. I've done a lot of good things. I recognize that my integrand was the function semicircle. I recognize that my radius was 2. I know the area of a semicircle is pi r squared divided by 2. I got it. Look at your bounds. Look at your bounds. My function is above the x-axis, so yes, my heights are positive, but look at your bounds. Your bounds start at 2 and go backwards. So what is your dx? You're going left, so your dx is negative. What happens when you multiply positive times negatives? Negatives, add a bunch of negatives, what do you get? Negatize. All right, so now you're used to this. Okay, you know what the integrand is. The integrand, there's the heights. The heights go from -2 to 2. Oh, I'm not going to get me again. I'm going to check out my bounds. Which way are they going? Oh, crap, they're starting at 1. All right, so I have to start at 1. Oh, how am I going to do? Oh, wait. I'm starting at 1 and stopping at 1. So yes, my heights are positive, but what is dx? I didn't need my graph. I don't care what my integrand is. If my limits of integration, that's another vocabulary word for you. Limits of integration, the bounds, the start and the stop. If they are equal, your integration value will always be 0. How about the last one? Integrand is still the semicircle. Above the x-axis, oh wait, no, it's not just the semicircle. It's 3 times the semicircle. Crap. Oh wait, that's a constant. Multiplying that. Osmosis. Take the 3 outside. Start at -2. Stop at 2 with a height that is your semicircle. Your widths are going in the positive direction. So your function height is positive. Your dx's are positive. It's the entire semicircle. So it is pi r squared over 2 times what? Wow. Pretty good, right? You've just integrated. Congratulations. Using a combination of properties and geometry. Even in May, you're going to, after you learn all kinds of fancy ways to algebraically do integration, you don't want to. You don't want to use fancy calculus on those. Recognize what you've got. Hey, that's a geometry shape. I don't need calculus. Hey, my integrand is at a constant height, right? That's just a rectangle. Okay. This is a practice handout that is linked on our Canvas page. And we're going to go through this one together. Okay. Props practice. So, given a random function, f of x is unknown. G of x is unknown. I don't know. So even after I know how to integrate, AP is going to give you problems like this. So they are just testing your knowledge of properties and non-properties. So look at this one. The integral of a sum is the sum of the separate integrals. And I'm going to get sloppy and just write g and h. I should write g of x dx and h of x dx, but look at the top. What is the value of the integral going from -1 to 6 of g? What is the integral going from -1 with a heights of h from -1 to 6? Done. How about this one? Osmosis. 2 times the integral -1 to 6 of f minus the integral from -1 to 6 of g. What are you going to get? 7 times 2, which is 14, minus g. -1 to 6 of g is 11. Done. The trap. It's a trap. R.I.P. Admiral Akbar. It's a trap. The integral, what they want you to do is look at f, which is 7, g, which is 11, and say this answer is 77. You do not have, this one is not possible with the information given. You would actually have to told what g and f are, and then you would have to try to integrate it using integration techniques that you don't know yet. And notice, try. Can you scan the rest of the problems and see, is there another one that's not possible? F, right? You do not know how to integrate. There is no rule or property for integrating a quotient. There are some techniques that might work, but you do not know those techniques. And even if you did, you can't do the techniques if nobody tells you what the function g or the function f is. Some people might look at E and say it's not possible, but that's a trap. This one is definitely a trap. That's not a quotient of 2 functions. That actually is 1/5, which you can osmosis. outside of h. So what is h? H is -5, but I'm supposed to multiply it times 1/5. So I get -1, right? Right? No, not right. What did I not look at? What's going on? Look at the bounds. The bounds are going the wrong way. 6, starting at 6 and going back to -1 means your dx's are negative. So negatize your result. This one gives kids a lot of problems. AP loves this. The integral of a sum is the sum of separate integrals. My bounds are going the right way. I got the first part. -1 to 6 going the right way of the function f. Look up here, that's 7. And then, what is this? Remember, 2 is your height. Default back to a graph. Start at -1. Stop at 6. Your function is always at a height of 2. I don't care what your dx is, other than your dx is positive, and so is your function positive. What's the area of that rectangle? A height of 2 times the width of 6 minus -1. So that's 7 plus 2 times 7, or 21. Pretty cool, right? You're going to need that thinking for this one. Given that the integral starting at a and stopping at b of some random function h is 2a minus b. Now this is a separate function from number 1, right? Number 1, this is, I'm not dealing with, I know this says h and this says h, but this is problem 1 and problem 2. They are separate. Find this integral. Well, again, the integral of a sum is the sum of separate integrals. Well, you know what this is, right? The integral of a to b of h of x is 2a minus b. So this part is 2a minus b. And then you need to add, think back to what you did up here. When your integrand is a constant, that is your height, think about your graph. Go from A to B at a constant height of what? That is the area of a rectangle. How do we get the area of the rectangle? It was height times width. This width was 6 minus -1. What is this width? You want the width to be positive, right? Because you went from A to B. So how do you find out that distance? Clever, clever. Now what is this? So this is just 2a minus b plus 3b minus 3a. Combine like terms. And what do you get? Ta-da! I feel so smart, right? Right? Let's do some more. Turn this sheet over. Now, this won't normally be capitalized. Notice on your paper, it's not capitalized. I capitalized it because you can't do this function. You can't do this problem if you don't know what an odd function is. And why would they tell you you have an odd function if you didn't need that information? This is going to be very similar to one of the homework problems we give you on evaluating integrals, handout number 1. Given an odd function, okay, odd functions are symmetric around the origin. Now, what information are they giving me? Going from 0 to 3, my integral is 4. What does that mean? I have some function, I don't know where it is, but let's pretend it looks something like that. Going from 0 to 3, what is the integral? So the function's always above the x-axis. This integral is 4, isn't it? Right, do you see that? Going from 0 to 3. Now, in reality, this function may go both above and below, but why not draw the simplest case possible? Right, 0 to 3, adding up all those infinitely small areas of all those infinitely thin rectangles, I get a 4. Hold the phone. Look at the next statement. If you start at 0 and go to 5, your integral is negative. How could that be? If you had a total of positive 4 going from 0 to 3, how can going from 0 to 5 get you a negative number? Okay, yeah. Something's, you got to be below the x-axis, right? How much below? G of x values are negative. You know your dx values are positive, so your function has to be negative. What does the integral from 3 to 5 have to be if you've already got positive 4 going from 0 to 3? Oh, snap. That has to be that integral has to be negative 6, right? Positive dx's, negative function heights, I get a negative 6 going from 3 to 5. Because now what happens when you go from 0 all the way to 5? You add 4 and negative 6 and you get negative 2. Check. Whoa. Why are they asking? I don't have any information about negative 3. What the heck? I don't understand. Stress, anxiety. They only gave me information about 0 to 3 and 0 to 5. How in the heck can they ask me to integrate with negative 3s and negative 5s? What the heck? Hello? If the function is odd, and this is what I've drawn in order to get my negative 2, if I've drawn this to the right of the origin, what do you draw to the left? And what would those integral values be? Oh, snap. This wouldn't be negative 6 because now the function dx is going to the right. Function values are positive. This is going to, but it's the same quote unquote area because of symmetry. One is below the x-axis, one is above. So what's true about this? It's not going to be 4. What is this? Oh, my Lanta. So now can you answer this with that picture going from negative 3 to 3? Start at negative 3. Add negative 4 to positive 4. What do you get? Hello. But how about starting at negative 5? and stop at -3. Hello. What is this? The integral of a sum is the sum of the integrals. With the same bounds, with the same limits of integration. Hello. -3 to 0. What is that integral? -4. And then I'm used to this. This is just a, oh, that's not a constant. Oh, snap. What the heck? Right? When in doubt, don't panic. Default back to a graph. From -3 to 0, your heights come from 2x. Hello, Algebra 1 kids. What does the graph of 2x look like? A line, a diagonal line with a slope of 2. What is the y value when x is -3? What is the y value when x is 0? What is that shape? It's a triangle, and I know the area of a triangle is 1/2 base times height. You're going from left to right, start to stop, so your dx's are positive. What are your heights? Your function values, so you're going the right way through the domain, but your heights are negative. So the true area of that triangle is 1/2 base. How long is that? Times the height. What is that? 6, but the height is negative. So that is -18 over 2, aka -9. -4 and -9 on Tuesdays is -13. Psych on every day. I just like to say Tuesday. I don't know why I like to say Tuesday, but I do. This is a very similar problem to what we just did without the odd piece, right? If 0 to 5 of f of x is equal to 10, whatever that is, that's a 10. So they want to know what is the integral of this sum. The integral of a sum is the sum of the integrals. They told us that this one was 10. My integrand isn't a constant, but it's almost as good as a constant, because what happens when you draw the graph starting at 0 and stopping at 5, where your heights come from the function y equals x? What geometric shape do you get? Going from 0 to 5 means your dx's are positive. On 0 to 5, the function y equals x is also positive. So the area of that triangle is 1/2 base times height. And you can literally just leave your answer like that. I mean, you can get a decimal, you can get you can make that a common, right? It's not that hard, but you can just leave it that way. You don't have to simplify anything. All right, last problem, number 5. Given a function below, the labeled regions have area, which means whatever P is positive, and Q is positive because they said they are areas. But notice the integral involving P is not positive, right? Do you see what I'm saying there? All right. So let's find, they're not asking for area, they are just asking for the integrals. So what is the integral going from 2 to 14? Dx is positive, right? 2 to 14. Function is positive. Notice that function has a corner. I don't care. I care about that for differentiation. I don't care for drawing rectangles and adding up their areas. They told us what that area is. What is it? Well, they didn't give me a number, but what is it? Q, right? So this whole piece is positive Q multiplied by 3 minus, well, look at this. Going from -1 to 2, no, I'm not stopping at 2. I'm continuing all the way on to what? 14. I'm going to break this up using that additive. The integral going from -1 to 14 is the same as going from -1 to 2 of my function, and adding, going from, since this is a 2 to 14. Now here's 2 traps coming up. Going from -1 to 2, the area is a positive P, but I didn't ask you for area. Function dx is positive. Hold on 1 second, sorry. The area P is positive, but they're asking me for an integral. My function values were negative, dx was positive, so the integral going from -1 to 2 is negative P. And going from 2 to 14, dx is positive because you went 2 to 14 is going to the right through the domain, but your function values are positive. This was a Q. And I had a 3Q here, but be careful. This is 3Q minus all of this. So it's 3Q plus P minus Q, or 2Q plus P. Oh boy. AP loves these problems, right? Because it really gets to the conceptual understanding of what you're doing with an integral. An integral is a sum of products. And those products are function heights times infinitely small widths, dx, traveling through the domain x. All right, good job. I will see you in our next live session.